I suspect so. So I just don't see it on my laptop anymore, but at least you will get to see it. All right, so my name is Mathys. I'm from the University of Colorado, from the Department of ECEE, Electrical, Computer, and Energy Engineering. And we have been running entirely software-based communications lab for probably about 10, 15 years. It started actually about 2001 with it. That lab was based on just using MATLAB without having hardware for free space communication. And we're now in the process of moving this to GNU radio and actually using free space transmission. And also to use it both in the theory class for communication as well as in the communications lab. You will see a little bit more about that as we go along here. So let me shift this to presentation mode. Okay, some stuff that you know already by now. SDR revolution occurred roughly over the last decade, and we do have now a lot of hardware and software available that is affordable for the student. Okay, that's kind of important. And low end, the $10 Realtek kind of dongles, and the higher end, the Mathys Research USRPs and so forth. We are using currently the HEC-RF as something of a middle ground for education and USRPs for doing research, which is another thing that we also do. Typical RF frequency from about 10 megahertz to the single-digit gigahertz, 6 gigahertz is a typical one. That's kind of important as we go along to realize that range and also to see that that may or may not be compatible with what we want to achieve. And then software choices, GNU Radio, MATLAB, Simulink. There were a number of discussions that we had, and a number of people felt that MATLAB, Simulink was the safer way to go, especially because they knew already how that works. And I've been trying to push towards the GNU Radio side and Python and so forth, because I feel that's really the way to go. That's the modern way of doing it. All right, so there's some internal politics there that that we had to work on. An interesting question is, from an educational point of view, have SDRs really changed fundamentally what we are doing in communications? And the answer is, of course, no. What has changed is how we go about implementing those things. We can now, using digital signal processing, we can now make waveforms that are way more precise than we could ever have made with analog circuitry, and that enables us to pack ever more information into waveforms. And so we can be more bold in terms of what we say that we want to do, and of course that has some repercussions in how we're going to teach about those things. Okay, one goal of using the GNU Radio in the classroom is to expand the GNU Radio user base in size and diversity. GNU Radio is affordable, I mentioned that already. It's very sophisticated, actually, once you look at it. It's in some sense even too sophisticated for the purpose of teaching, because you have to be careful not to put something in front of the students where they think, I'll never get it anyway, so I'm not even going to try. Okay, it's open source and expandable, which is of course a big plus. One of the big things that is way better than using the MATLAB Simulink platform. And it's a great tool to visualize the effects of digital signal processing, in real time and ask what-if questions. Okay, and here's where I think I have an example, and in fact I have the example in live GNU Radio. It's a little tricky here because I don't see the screen here. I don't seem to be able to have the screen on here as well as there. So I have to look over there for getting into this. And I think I also lost my icon here for GNU Radio, but here it is. Okay, so what you see here, and it's of course pretty small. I might be able to see myself hardly here on the screen. What I've been putting up here is a sine wave generator, a rectifier, a throttle, and a buoy sink. If I'm running this, and my cursor here, okay, there we go. Then I see the frequency display. If I go into the time domain display, we get to see the full wave rectification, and there is a little button up here where I can say a full wave to false, and then I get the half wave rectifier. Okay, that's a pretty basic component, of course, for electrical engineering. But the interesting thing now is, I'm going to put this back to full wave. You get this picture here in the frequency domain, so the fundamental frequency, so the DC component is here, the fundamental frequency is here, and the second harmonic, third harmonic, and so forth. I use the 1 kilohertz frequency, so this is spaced 1 kilohertz apart, 2 kilohertz apart because of the squaring. Okay, now if I change the full wave here to false and make the half wave rectifier, I get those additional components in here. So the interesting question is to ask the students, well, why do I get this in the first place, and then what implications does it have? And then if you have ever built a power supply, if you use just one diode for the rectification, then you have to have a much larger capacitor in order to get the same low ripple than if you do a full wave rectifier. But if you do a full wave rectifier, you have to use 4 diodes. Okay, so there's a trade-off there. And it really comes from that we have those additional components. And the interesting thing is that you only get them down at the fundamental frequency. You don't get all the other components. You just get the even numbered harmonics. You don't get any sort of numbered harmonics in there. So it's kind of interesting to play with that and to be able to just click on the button like I did here. And in that case, when I do it in class, I can actually see it on the screen, and it's a little bit easier. So at any rate, I'm going back now to the presentation here, and we'll do Shift F5. And so the next interesting question is, where did that rectifier block actually come from? Okay, this is the old-fashioned transistor kind of thing that we used to have on crystal radios, which gave the name to the crystal radios. And the rectifier FF is actually out of 3 modules. Okay, so in order to do the full wave rectification, half wave rectification, I built this module. In fact, it went a little bit the other way around. I wanted to learn more about GNU radio, and so you start out with the square FF block, which is on one of the tutorials, and then you want to do a little bit more than just the square FF, and so the next thing was to actually make that rectifier. Most of you probably have been playing with our OT modules, and you know a lot of that stuff. So the GR mod tool is the thing that we use to set up the structure for an OT module. Then the main components that you have to do yourself is the quality assurance part. I did it in the Python file, QA thing here for the rectifier. Then the public header rectifier, the public header file, implementation header file, which is derived from the public header file, implementation source file, and the XML block. Okay, so that took me probably about a week or so to really get this going using trial and error, because when you just start with it, there's a lot of things that you just don't know for sure. You deal with Linux, you deal with C++, with Python, and God knows what. I'm pretty fluent in MATLAB, but not in some of those other languages. As an example, here's the work routine for that rectifier. So you see here there is a flag, full wave, and if it's full wave, then I just take the negative part and make it positive. If it's not full wave, then it's half wave, and so I set the output to 0. Only non-zero if I'm positive, and otherwise I set it to 0. So it's a pretty simple thing, of course, to implement there in the work routine. The major portion of actually making the code goes into a lot of those other things and making sure that we don't make any typos. Here's the test function. In fact, I have found in doing those OOT modules that I spend a lot more time on actually making the test, the quality assurance test, than the actual routine itself. Now, I've only been making simple routines, and when you make something more complicated, then you're going to spend more time in the work function as well. But it pays off to do actually the quality assurance because most of the time, the first time around you run it, it doesn't work, and then it has already paid off because you have found an error that you then correct before you put that into your new radio companion. Okay, so why would anybody want to write their own modules? GNU radio is a work in progress, so what you want may not be in there. Then there may be just aspects of doing education, which is different from doing research or from deploying systems. And so you may just want to have maybe even an existing block, but repackaged in a way that fits better for the way how you're teaching the communications class. Then, not to overlook, it's a great way to learn about GNU radio. It's not painless, but it's great. Typical question, where can I learn how to do it? It's a bit of a sticky point because there are some tutorials, but usually you get, like from the ground up to a certain level, and then you start asking what if questions, and then you're sort of out in the void. Okay, there is the friendly folks at the Discuss GNU Radio mailing list where you can ask questions, and that is actually working quite well. It has been overflowing my inbox, but otherwise it's great to have that support. Then the next thing that I think I want to talk about here is what actually does our curriculum look like and what is it that we want to achieve with it. So we have what is known as a communications track. It's a 2-semester sequence for seniors, and it consists of ECN 4242 communication theory and ECN 4652 communication laboratory. So the two courses are related to each other. The 4242 is a prerequisite for 4652. The prerequisite for the communication theory course is the linear systems class and probability theory. Now, those are both classes where students feel like, why do I pay so much money and I have to do such difficult things? Okay, and so they come into the communications class and they don't really know what to do with that. All they know about is that there was kind of a bad feeling about probability theory, and the sampling theorem didn't also go that well. And so what I do in the communication theory class, the first one that they take, I have to go, of course there's an introduction, but then I have to go into linear systems and I actually have to do a review of linear systems. We have to play with the fact that there's actually 4 Fourier transforms. A lot of communication theory books actually avoid the use of all 4 different variants. The 4 different variants come about because you can have time, continuous and discrete. You can have frequency, continuous and discrete. So you have 4 combinations. And the students don't, for some reason, don't really appreciate that initially. For them, it's all the same. You have a digital computer, but the music just sounds the same, like if you have some analog source, at least to full approximation. So I have to go and teach them about that. I spent probably about 2 weeks or so, or 3 weeks at the beginning of the course, just reviewing that. There is the issue of, for example, how do you design a filter. They have learned that there's brick wall filters in theory, and so they expect brick wall filters. And when you then work with the filter, you have to round the edges a little bit, take out your sandpaper, and specify things. Okay, then the modern way of doing communications, of course, is digital communications. But can we go directly and do digital communications? The answer is you have to have a basis in analog communications first before you can really go into digital communications. And so we do emphasize that here in the first part by going into amplitude and angle modulation. I've been playing with, for example, not do FM modulation, but it turns out that doing FM modulation is a good way of actually connecting the dots here for linear systems, getting them into digital signal processing questions, and asking again what-if questions, and we'll see a little bit of that. Then probability theory needs a review, random processes needs an introduction. We try not to emphasize that too much, not to scare away too many students. That comes about at the time, the semester, when there is the drop date. Okay? So you don't want them to all drop that course, otherwise, you know, well, you have more time for research, but the chair of the department is not quite happy if you suddenly don't teach anymore. Then noise in continuous modulation system, that's something where I don't really put a lot of emphasis to move on then to the transition from analog to digital, then digital baseband communications and digital bandpass communications. Now when you look at this and you think about using GNU radio instead. Okay, linear systems, you can simulate the linear systems, but and of course, you know, any kind of radio does need signal processing. So you can do this actually reasonably well in GNU radio. Amplitude modulation works fine, angle modulation works fine. In fact, the hello world of GNU radio, of course, is based on using the FM receiver. But then when it comes to the digital part here, digital baseband, you can't really do a lot in GNU radio. It depends a little bit on how you look at it, but we'll see as we go along that there is actually, I have to make most of the OOT blocks in order to make this work in a reasonable manner, at least in my opinion, in a reasonable manner. And then the digital bandpass communication that you can do, but in a way, GNU radio is actually too sophisticated for that, for the understanding that students have when they get exposed to communications first. Okay, so a little bit of what I just said is written here. The main goal of GNU radio, of course, is to control software-defined radios and not to teach linear systems or to implement baseband communications. So that's why some additional OOT modules were needed for the way I want to work with it. Okay, for learning communication theory, we need to start with small building blocks and piece them together into larger systems while retaining the ability to control the output of each of the building blocks. So I don't want to actually just put a full-fledged modulator block in there and tell the students, well, put bits in, and then at the output just connect it to the USRP or to your Osmocom sync. Because in this way, the students don't really learn a lot. I believe that most students can move blocks around in a block diagram, but then to actually know how those things work together and to form a picture, a mental picture of how this really works, that requires, in my opinion, a finer granularity and a little bit more work. You know, there's a book out there which is called Learn Python the Hard Way. So in a way, you know, this is learning communications the hard way by not just putting in a block that does everything for you. So here, it's just a simple example of some of the things that I did. Coming from the MATLAB side of things, diff, FF. Those are essentially, of course, the simplest FIR and IIR filters that you can get. So in principle, you can take the blocks that exist in GNU for doing that. But it's kind of nice to have those as individual blocks, which just do this particular function. And I use that in the beginning of the communications laboratory course because the students first need to learn the difference between analog and digital, and or actually I should say discrete time and continuous time. Because in the sampling theory that they have just heard that there is such a thing as the Nyquist frequency, so if I give them a 1 kilohertz waveform, then they think I just use a 2 kilohertz sampling rate and that will do the trick. Okay, but of course you're not going to get nice pictures if you look at this, and you're not going to further your understanding if you just work exactly at the Nyquist frequency. And so I tell them, for example, to take a sinusoid or a rectangular waveform and then do the com sum or do the difference, see what effect it has and what the sampling rate you have to use compared to the fundamental frequency to get reasonable results. Okay, and some of the others in here, power n, so I have a block where I can then use a slider to raise the power to the second, third, fourth, fifth, and so on, so that we can see what that does. One example where that comes in handy is when you have to tell them about the fact that we really want to use complex exponentials for representing signals and not just sine, cosine. Okay, so the nice thing is, of course, when you use the complex exponentials, you raise something to the fifth power, which just simply shifts the frequency over to 5 times the frequency, whereas if you do that with the cosine, then you get all kinds of products between frequencies, and you don't just only get 5 times the frequency. Okay, so here's an example of the sinusoid raised to the fifth power, so you can actually give them a picture like that and ask, well, to which power did I raise that? Okay, I have a live version of that, but I don't think it's worth going into it right now. So here's Guglielmo Marconi doing his experiments. And like I showed in the outline of the course, the first thing that we want to look at is amplitude modulation. So here is a block for amplitude, or actually a whole flow chart for the amplitude modulation. It's from my experience of having been sitting over there, you can't really read those things. So I was going to show you this one and then the next one and then tell you, well, find the difference between the two. But it's kind of hard to see it, so I have to point it out. So what I'm doing here is I'm having a signal source for the carrier frequency and I have a signal source for the actual message frequency. One of the things that I do in a simple example like that is I have to tell the students that we have to use multi-rate signal processing. Your signal source, which ideally, of course, is going to be some music or some speech or something like that, that's going to be at the sampling rate of, say, 8,000 when you do amplitude modulation. But your carrier is going to be at least 100 kilohertz, maybe 1 megahertz or so, so in order to make the two compatible, you have to move the sampling frequency high enough for the carrier, and then do the interpolating FIR filter to put your message signal up there. That's not something that they learn in the linear systems class, that's something that I have to introduce at this point in time. Okay, then I add the two together, so the textbook example of doing amplitude modulation, or one of the textbook examples, is to say we're going to take a message frequency, we're going to take a carrier, we add the two together, and then send it through nonlinearity. Because, at least in analog hardware, it is difficult to multiply things together. That is expensive. And so in the analog days of doing amplitude modulation, the typical thing was to add things together and then send them through nonlinearity. So the nonlinearity is this block in here. In this particular one, I use the rectifier again, so I can use either the half wave or the full wave rectifier, and then I can ask the question, is this going to produce amplitude modulation with transmitted carrier or with suppressed carrier, and at which frequencies is going to happen. I'm not going to go into all of the details here, and then the second version uses actually the power n with an exponent of n equal to 2 or n equal to 3, so that's the nonlinearity in this case. If you do the n equal to 2, then you get the AM ESP SC signal at twice the frequency of the carrier. If you do it at the actual frequency of the carrier, if you do it with n equal to 3, you get it at twice the frequency of the carrier. So those are interesting questions where the students can actually, if I give them the GNU radio, they can actually go home, do their homework, and also verify by playing it in GNU radio, is what I'm computing is that actually the right thing. In fact, the amazing thing about communications is that, especially when you do it digitally, is that how well the theory and the practice agree with each other. Okay? And that's one of the points that I want to emphasize when I teach those classes, in order to motivate the students actually to do the maths, because they have a tendency to just try things. I'm just tweaking this a little, and then when something comes out, they're just happy. If there's just, some spectral lines at some frequencies, even if that is the wrong frequencies and, the spectral lines come from aliasing, they will still turn that in and say that that is great. So with the GNU radio, I can give them actually sound signals, they can listen to them, they can hear if it gets distorted, and so forth. So that brings in an additional dimension of learning there. So this is Edwin Howard Armstrong's idea of a wedding present. That is the first portable radio. This is his wife, and she got that as a wedding present. Okay, so we're going into FM now with Edwin Howard Armstrong. This is the most complex thing that I want to show you here. And again, I'm not expecting that you can read that, but this is the Armstrong method of making wideband FM. Okay, that's of course not something that you would do as a mainstream idea in digital signal processing. You don't really need to do that there. That's from the analog days, but it is a very nice exercise in learning about frequency modulation, in learning why what the early pioneers wanted to achieve with frequency modulation, why that didn't work. They wanted to just, if you make frequency deviation of whatever 10 hertz, and so now you're only going to use a bandwidth of 20 hertz on a signal that, so that was 3000 hertz maximum. So you can demonstrate that, and you can also demonstrate of how, if you actually have an FM signal, how are you going to measure what your frequency deviation or your modulation index is, and so forth. And for this one, I do have a live version so that we can look at that, because you can't really see a lot from this diagram. So let's see. Put the Armstrong FM. So I can run this here. And again, you have to use multi-rate signal processing here. You have to upsample the baseband or the message signal. And so initially, you just see those straight lines and not much definition in them. So on the left, there is the narrowband FM signal. So if I go into this and I actually enlarge this a little bit, then you can see that I do have those. Pull this down so that you can see the frequencies. Here we go. So we have here 100 kilohertz for the carrier, and then we have a 1 kilohertz message frequency. So you can see that those two sidebands to the left and to the right of the main carrier, those are the plus minus 100 kilohertz. And this is actually a narrowband FM signal. If you look at it in the time domain, like this, you can see it's perfectly good FM signal with a constant amplitude. Of course, you don't see the FM itself in the time domain because it's way too little. Now, if I go on this side here, where I have the wideband, okay, so you can see. So you can see nicely the spectrum of the FM signal with DC component and the first sideband, the second sideband, and so forth. And I can change the frequency deviation. That's this slider up here. So if I go and I make this a little larger, you start seeing how the spectrum changes. And in fact, if I go here to 125, then you see that now I have the DC components, then I have the component at the first harmonic, which goes way down, and then second harmonic stays up, and so forth. And so you can actually now go, I have to go back to the slides here. Okay, so this is the picture that we just saw, the live version of. And we use then the Bessel functions, and we go and take a look. Here's the Bessel function with index 0, that's the DC component. So that one was high. Then the J1, that's the one at the first sideband, that one was small. So it's either here small or over here small. And then the J2, that one was high also, so we cannot be over on this side, so we have to be somewhere over on this side. The J2 is large, the J1 is small, which is here somewhere, and the J0 is large, so it's negative here, but when you see the spectrum, it's of course all the magnitude. And so we are roughly at about 3.8 or so is the modulation index, and then from there, you can compute what was the frequency, the maximum frequency deviation, and you can verify that with the components that you actually put into your block diagram. Okay, here's a picture of the two waveforms. You can see that it's not an entirely ideal signal that you're creating this way. All right, so now the communications laboratory. Here we start with continuous time and discrete time signals, and then we do the Fourier transform approximation, sampling theory, Nyquist criterion, so that we see the duality between Nyquist criterion and false amplitude modulation. Then random processes, power spectral density, pan receiver with matched filter. So all of this is basically baseband communications. And then digital baseband communications. And then we go into the software-defined radio here. I'm planning to move this forward. That was how I did it this last spring. Amplitude modulation, both suppressed carrier and transmitted carrier. And then amplitude and frequency shift keying, real bandpass and complex low-pass signals. That's one of those that I probably also will put in a little earlier, so that it works better together with the radio. And then comes actually the phase and hybrid amplitude phase shift being basically the signal constellations. So we're not really getting to very sophisticated communications, even though FDM is actually not in here because we just don't have enough time. And so what this means is that we need to work at the very basics of the digital communications, and one of the things that I found was missing is a way to just inject the message on one side, an ASCII text message, and then make this into a serial stream of bits, add some noise perhaps maybe to it and so forth, make it into a waveform, and then receive it again, and see whether you can get the ASCII text back and actually visually see that text. Okay, and so we built an old block which does that, basically a print character block, which will allow us to use that. This is Endo Modo, the baud rate kind of guy. So now here is the block. Let's see, I have to go to the live version to do this really in an interesting way. Serial. There we go. So if I run this, what we will see is what the idea is of using this. So I'm going to do this one here, and then oops. Okay, so what I'm doing here is, let's look at the time domain. Okay, so we have plus ones and minus ones. That's the serial data stream that we are transmitting. Then there is noise that I can add to it. No, in that particular case, it's not noise, but that's in the next one. This actually comes from a file that just has the bits in it. So I give the students a file that has bits, serial bits in them, and there is some mystery message in there so that when they do their signal processing right, that they get to see the message. They do not necessarily know the baud rate, they do not necessarily know whether a 0 goes into a -1 or a +1, and so forth, and they have to then figure those things out. So here's what I have here. I have to see how to control this. I can now change the bit shift because, of course, there's the question of how do those things synchronize, or where is the start? The first bit of your ASCII code. So I can shift this over. You get to see over here how things change, and then magically, once you have the right thing, you actually get to see a message that's readable. Okay? So I think that is important to do that for students to make them believe into communications, that you are not just having some random signal that you put in and then you look at the spectrum. You actually want to have a real message, and they really like to work on those things when they know there's a message coming out at the end. And so that's basically a block that we made so that students can do that. So let's get here closer to the conclusion of the whole thing. Go back here. This one. Okay, so that's just what we saw there live. And then I have one demo where they are doing this whole thing with the addition of noise. And so that they do a rectangular one, then they use the matched filter, so they get the triangular output. And just very quickly, the GNU radio installation. We did several attempts. What we ended up doing is putting it onto a USB stick, actually just similar to the one that we received here. That worked best, also to hand that out to the students. Some of the daunting things when you do that, and most of you have gone through that, there's lots of different pieces that have to come together so that you can actually write all key blocks. Some of the blocks that I used as examples to get up to speed. And the conclusion, GNU Radio is a great addition to that undergraduate curriculum. It's important to introduce it early on to the next generation of communication engineers. It must be working in the student environment with a minimum of hassle and overhead, both for my own sake as well as the sake of the students. The building blocks must be simple and their function must be transparent. A lot of blocks are difficult to understand when you first see them in GNU Radio. It's not a criticism, it's just simply because people try to pack many things in there so that they can do bigger things than what we do in education. And then actual text and audio signals should be used whenever possible to emphasize that this is actually applicable, not just abstract random signals. Okay, so that's it.
Yeah, I hate to rush at the end there, but because I think there's like a really great conversation we can be having. Unfortunately, it's past 5 o'clock, so and I know people probably we're not coming out tonight or need to go back to our hotel, you need to go home, you know. But I really thought that was a fascinating lecture, and there could be a really great conversation about education and modern communication systems, and et cetera, et cetera. But before I wrap it up wholesale, just is there any like quick thought or question that we can have Peter address? To get out right. This is
Right.
Are any of your labs and examples available on web?
Yes, they are. I'm going to put up, I'm going to submit this presentation. I can put the URLs for that at the end of that.
Are you seeing your students get more successful with the goals?
It's too early to tell, but certainly when with what we do with the MATLAB stuff, that has helped them to get jobs. First of all, they got to know MATLAB. Second, they really find that the theory course doesn't really bring the communication theory home to them yet, but once they have gone through the communications lab, with making the waveforms, with getting waveforms and having to extract those mystery signals and so on, that has helped them a lot. That's the feedback that I'm getting. So now I'm trying to move that a step earlier into the communication theory as well, in order to hopefully make them get the whole thing earlier, not just in the communication lab, but in the theory course as well.
Okay, we should wrap this up, but let's thank Peter once again.